Hello and welcome back to part 2 of U sub in... Oh, I didn't say the class. Yeah. Hello and welcome back to Calculus 1, section 5.5 U sub, and this is part 2. Okay, that's much better. So in this case, we are going to take a look at some spicier problems and also something that is called back substitution. Now, before we jump into any of that, I just want to remind you real quick of what U substitution was in the first place, and then we're going to deal with the, as I said, spicier problems. So let's take a look at the problem integral of cosine of 2x plus 5 dx. And this is just, for us to kind of warm up. So we said that this is what happens in your head, right? Oh, I know how to deal with the cosine x dx. So if I could just make all of this to be one variable, and yes you can, right? U equals 2x plus 5, and then because you have to change dx as well, immediately du is equal to 2 dx. Now from this point on, you can either move the 2 under du, or you can fix the problem with 2 and the 1/2. It's completely up to you, the way you would like to do it. That's 1/2 integral cosine u du, because 2 dx is du, and then u is just the stuff inside the cosine. So the whole thing now is a simple 1/2 sine u plus c, and then you put x back into the problem. So 1/2 sine 2x plus 5 plus c, and you call this problem done. Now, you might be skeptical about this, in which case you do the check, which is simply the derivative of your answer. And if you get original problem back, that means you're good to go. So the derivative, you copy 1/2, derivative of sine is cosine of 2x plus 5, and then you have to multiply by the derivative of the inside, which is a chain rule, which is times 2, and then plus 0 for plus c, the derivative plus c. At this point, 1/2 cancels the 2, and you have your cosine, right, which is where your problem started, as you can see up there, right? That's where the problem started, in cosine 2x plus 5, with nothing else around it. So we know this solution is good because we checked, and we're going to now take a look at some spicier cases. Now, the book is giving you about 100 exercises to practice. It's more like 85, but there you go. It is extremely important section because it will be used in Calc 2 a lot. So, yeah. Now let's take a look at this not too frequent, but it did pop out a couple of times in Calc 2 and Calc 3, maybe once or so. It's called back substitution. Back sub. And it's a little bit weird, right? Because so far we are used to just replacing all x's and dx with what we get in a substitution, and we're done. Well, this one is a little bit different. You see, this is like one of the standard problems you practice this on. You have the square root has x minus 1 underneath, and again we go and we say, well, I know how to deal with the square root of x, but I can't really deal with square root of x minus 1. So your natural substitution here is u equals x minus 1 to fix that square root, which immediately gives you that du equals dx because derivative of x is 1, derivative of negative 1 is 0. So you just have du equals dx. And when you try to plug all of these things in, you see that this one does not have its substitution. So if I have x root u du, and that's bad because I can't have any x's once I switch my integral into u's. And the back substitution is right here when you write that x is equal to u plus 1 and plug that in here. So this is where the back substitution happens. Right? This procedure here in orange is known as back substitution. So now we actually have a basic integral when we distribute the, if you write your square root as u to the 1/2 and you just distribute that into the parenthesis, you get u to the 3/2 plus u to 1/2 du. And now these are basic integrals on which you can use your n plus 1 formula. So if you remember your integral of u to the n or x to the n, whatever x to the n, dx was x to the n plus 1 over n plus 1, and that included the roots or whatever, right? So you definitely have u to the 5/2 divided by 5/2 plus u to the 3/2 divided by 3/2 plus c. Because all I need to do is to add 1. So 3/2 plus 1 is 5/2, right? Because you are adding 2/2 to it. So we're using just the basic formula we know from before to deal with this. And now we just deal with the double fraction by flipping these fractions in front of u. So that's going to be 2/3 u to the 3/2 plus c. And now we bring x back, and that was x minus 1. So 2/5 x minus 1 to the 5/2 plus 2/3 x minus 1 to the 1/2 plus c. It doesn't look pretty, but it doesn't have, oh, this is a 3/2, not 1/2. Exponent 3/2. Right? It doesn't look pretty, but hey, not everything looks pretty. So that's okay. We have the solution, and as I said, we used the back substitution method where we had to solve for x and plug it back into the equation. It's not something you can always use, but you know, keeping this in the back of your mind when you run into these issues. And clearly, right, in this case, we did not have function derivative pair, so that made a lot of problems for us, right? There was no function derivative pair in this case because the derivative of x, pick any x you want, the derivative of x is 1. So you can't have the derivative of 1x to be the other x. Right? Derivative of x squared is 2x, so that's fine. But when you have x under the root and x outside of the root, it doesn't work. No bueno, right? So that's the back substitution, and I think they should have a couple of these exercises where you can do this. And yes, problems 78 to 86. So they have 9 exercises for you to practice this skill. And I'm wondering why 86 is in here, because it's not. That one is weird. Whatever. Yeah. Let's take a look at one more of these back substitution, and then we'll take a look at some regular substitution problems. Well, there's one with the cube root, there is one with the, let's try 80. It looks mean and evil. Y squared over y plus 1 to the 4th dy. I mean, in a problem like this, it's obvious what u must be, because it could only be one thing. What do you guys think? Nope. Yeah, it's usual when you have the denominators, usually it's whatever it's in denominator, because it cannot create the du part for the numerator in that case when you do the derivative. So it's usually denominators. And du equals dy. And now when you try to do your substitution, you have u to the 4th downstairs, you have your du, but now you see that you have y squared on top. And that's where the back substitution kicks in. Y is equal to u minus 1, which means that y squared will be u minus 1 squared, which means that y squared is u squared minus 2u plus 1. So u squared minus 2u plus 1. And this now breaks into 3, right? When you divide each one of these orange terms with a u to the 4th, it breaks into 3 separate. So you get u squared over u to the 4th, you can simplify, minus 2u over u to the 4th, you can simplify, and plus 1 over u to the 4th, that's simplified already. So you get your integral of 1 over u squared minus 2 over u cubed plus 1 over u to the 4th du. And again, the same formula integrates here. The x to the n, right, that goes into x to the n plus 1 over n plus 1, because each one of these can be written as a negative exponent. So u to the minus 2 minus u, 2u to the minus 3, and then plus u to the minus 4 du. So they all can be written in the form for the basic power rule. And now when we integrate, we get u to the minus 1 over minus 1. Remember, you are adding 1. Minus 2 times u to the minus 2 over minus 2 plus u to the minus 3 over minus 3 plus c. Now you simplify this. Negative 1 over u. Negative and negative cancel, so plus 1 over u squared. And then minus 1 over 3u cubed. Plus c. And remember, your u was y plus 1. U was y plus 1. So negative 1 over y plus 1 plus 1 over y plus 1 squared minus y over 3 y plus 1 squared cubed plus c. Ta-da! So it was back substitution again, and it made it work. Questions, concerns? Yes. Yes. Well, we do have the function. That's exactly y plus 1 is a function. Well, it depends on how annoying it is. We need to have all of the other players for substitution to work. Not every integral is use sub, but if you have nested functions, you better have enough of the derivatives present. Yeah, enough derivatives present to counter each one of those. Well, there are, you know, for something like that, because you're now putting in the square, there is also like you can FOIL it out, see what you get, and then if you have enough, maybe for even basic use sub. But then again, there are two techniques you haven't learned: integration by parts and partial fraction decomposition, both in chapter 8 in Calc 2, which take care of situations like that when you have y squared plus 1 is non-factorable. It's like a prime quadratic, and it has its place in the setup for partial fraction decomposition. Now that's next semester. So a lot of the what if scenarios will depend on also what the problem looks like, and if that integral is covered in Calc 1 or it's covered in Calc 2. So if you, let's say you run into a specific problem in your Calc 1 homework, then we can definitely work on it. But we can't run hypotheticals here because you literally know like 3% of integration, you know, where, you know, Calc 2 is coming up, Calc 3 is coming up, right, to fill in the blanks for all of the other stuff that you haven't learned yet. So it's very difficult to play the game what if with only two sections, basic derivatives and U sub, where we have like a whole chapter just on integration techniques coming up. Yeah, they should be. You should be able to somehow algebraically manipulate, and this is what I want to go now over. This is harder examples that are not obvious. Some of them will have nested integrations by part. I mean, I have seen some linear operators that you learn in graduate school that have 4 nested integrations by part inside, and it takes you 40 minutes just to, you know, well, that's integration by parts, and each one of those integration by parts has its own U sub. So it takes like 40 minutes to you know, go through that. And then some problems will be basic. I think I actually have a very good example from differential equations, which is also considered like calculus 4, where I did use I think it was in here. Let me just jump up real quick. Yes, it was for convolution. Good. So to solve this integral, here I am using basic U sub, right? And this is just like working out e to the at integral, and I used the U sub for this problem, and there was another way through Calc 2 to solve the same problem. So I avoided the longer procedure so I can use a basic U sub from Calc 1 to solve this problem in 3 lines, where the other procedure will take you know, half a page or more. So it all depends on, as I said, how far you get with your right, with all of the methods that you learn along the way. Let's see. All right, so here is another one. This is one of the standard problems. Like, this showed up so many times on exams and final that I don't even want to count. Sine to the 10th power of x cosine x dx. Function derivative pair, where your function ends up actually eventually being your u sub. So do you see a function and its derivative anywhere? Very good. And that's immediately how we know that u equals sine x, du equals cosine x dx, and then we plug all of that in, and it just collapses into this. The entire trig problem immediately collapses into this joke, right? You have to have the trig as u and the trig as du as a derivative in order for this to completely remove trig out of your calculation. So why did you pick sine? You picked sine because sine was raised to the 10th power. So you needed a single cosine to leave it in. I usually say to my students in Calc 2, you leave cosine in a bank, right? Because you need that for dx. And then you can see your cosine x dx making a du. And then you have your sine is u, so sine to the 10 is u to the 10. And now it's joke, right? Once you have this, it's just u to 11 over 11 plus c, and you swap out. So that's 1 over 11, and instead of u, you have your sine to 11 x plus c. It's a very quick problem, and I just immediately want to contrast that to this one, integral of x squared sine x cubed dx. So now you see that your function derivative pair is shifted from trig, because you can't use trig because there is no matching trig for dx, for du, I mean. So in this case, right, what would be your function? And what's the derivative? Okay, well, we'll just have x squared, but yes, when we do the careful derivative, we will get 3x squared. So very good, and then du is 3x squared dx. I don't have the 3, so I'm just going to fix that by multiplying by 3, which is what I need. I need 3x squared dx for du. And now the problem becomes 1/3 of, and now see the sine survives, right? Because we never replaced anything sine, right? It was all polynomials that we replaced. So it's sine of u du. Where in the previous example, we replaced sine with u. In this case, we only replaced the argument of the sine. We did not replace the sine. So this becomes negative 1/3 cosine u plus c, which is negative 1/3 cosine x cubed plus c, and we are done with the problem. So I hope that you might link these two problems and see that in some cases your trig gets replaced by the substituting functions, and in other cases it does not. It depends on what kind of a pairing you have. And in our case, the pairing was through polynomials. So we picked u to be x cubed, and its derivative x squared was floating about, which was great. And we just fixed that real quick, and we're done with the problem. Let's pick out another spicier case. Well, this is actually easy definite integral, but you know, it's practice, and I know it's probably gonna trigger some of you, knowing that your lower limit is ln of pi over 4 and the upper limit is ln of pi over 2, then you can imagine what kind of a problem you're getting. Well, you need to have some cosine as well. There we go, for good measure. So try this one on your own for a few seconds. No pressure. Any ideas? That's okay, that's okay. Can you tell me at least what u is? The substitution? Okay, good. So e to the w, which means that the du is e to the w dw. Okay, so if anyone is struggling with that part, there is that, and let's go. Yes. Well, you only have basic sines and cosines of pi over 2 and pi over 4. The answer to your question is yes, but you should be able to take those without a calculator. I hope. Let's see, actually. Maybe there is something that I I had the oversight or something. Let's see. So we start by transforming this. So EW dW is going to be du. And then I just have a cosine of u in front. And we need to work on these limits. And this is one of the greatest things about the definite integrals in the u sub. You can transform your limits into u domain, and then you don't have to go back later, because you're just computing definite integral. You can compute it completely in your domain and be in u domain and be done. So that is now done by simply using your formula E equals EW, and then understanding that the bottom over here is W1 equals ln of pi over 4. So you plug that in. What you get is the U1, which is the bottom limit. Remember, your integral is U1 to U2 some function of U du. So everything should be matching as U, right? So that's why I'm switching these. These guys over here are W1 and W2 because the main variable of the original problem is W. Now, when I do my substitution, the main variable is going to become U. You see a function in terms of U. So I need U limits over here. All right, so let's get rid of all of the purple now and calculate this. So what do I have? I have simply e to the ln of pi over 4, and then eln cancels, so I just have pi over 4. Okay, that's just pi over 4 now. And u2, which is the upper limit, is e to the ln of pi over 2, which is, when eln cancel, just pi over 2. So now I don't have to go back into w variable. I just solve everything in terms of u and I'm done. Integral of cosine is sine of u computed from pi over 4 to pi over 2. And that is sine of pi over 2 minus sine of pi over 4. Again, basic values, root 2 over 2, which if you want, you can put on a common denominator or can keep them separate. It doesn't really matter. It's the same amount of operations, so you know, whatever you like better. But this is the exact answer for this problem. Questions, concerns, anything? Yes? That's why I underline E times dW is E times dW, which is this du. So that's all on a pile. Cool. Okay, that's good. What else? For all of them, because if it's definite, which we're going to do another example right now, if it's a definite integral problem, you will always be able to switch, because now you have 0 to 4 x over x squared plus 1. This is the integral that will frequently show up in Calc 2 and differential equations because it's one of the solutions to partial fraction decomposition, which is used a lot in those two courses. So this integral is very frequent, and without that x on top, it will be just simple inverse tangent, but we have x on top, so it's not. Right? So we have to work on this one. Okay, let's see what you guys get. If anyone wants to at any point offer the U substitution that is being used, that's fine, because there's still a lot more work after that. I mean, technically there is only one thing that U can be in this case, right? Yes, x squared plus 1. There's literally nothing else it can be, because if you take a look at the numerator, it's just x. You can't just say U equals x, because that's just swapping x for y, literally, right? So having this and then having your du 2x dx, you don't quite have 2x dx, you just have x dx. So that has to be fixed, then the limits have to be fixed. There's a lot of stuff. You're talking about this part? So when you have your when you pick your U substitution, then you are supposed to take the derivative in respect to x, which it will be 2x, and then we move dx to the other side and becomes 2x dx. Now, since we don't have 2x dx, we have to fix that. There we go. And you can only fix numbers. You can never do this with variables. It's only constants, numbers, because they can escape integration, go in and out of the integral. Variables cannot do that. Okay, so now we have more work, right, to do, because we have 1/2 integral, and now the top is du, the bottom is u, but we have to change variables, so I think I used purple. So now I need my u1 and u2 using this. So what is u1, the lower limit? Very good. And the u2 upper limit? 17. Very good. So we get those by taking these limits and just simply stuffing them into x one at a time. So 0 squared is 0, plus 1 is 1, so that's a lower limit. And then you have the upper limit, 4 squared is 16, plus 1 is 17, the upper limit. And now we don't have to go back into x's. We just compute the entire integral in terms of u. So 1/2, what is the integral of du over u? Excellent. It's ln absolute u plus c. Well, we have computed from 1 to 17, but yes. Okay, so now we plug in these values, so that's going to be ln 17 minus ln of 1. Now ln of 1 is 0, so we just have 1/2 of 17. There we go. Okay, so one more problem and we're going to switch to exam review. Hopefully you have some good questions and things. Let's work on problem 62. I'll give you some time to try and work it out on your own. 0 to 1 over 8 of x over square root 1 minus 16x squared dx. I think the choice of u is obvious, right? Is it? Yes. Which makes du negative 32x dx, right? Okay, let's see how you figure these things. Would anyone like to start? Should we go over this together, or you guys got it? So do you have the negative 32 filled in and negative 1 over 32 in front? ln. Hold on, this is du over square root of u. It's not a single u, which means it's not ln. That's why that's why it doesn't work, because probably you had that. Did you switch the limits? So what is the u1 lower limit? Perfect. Perfect. And the u2, which is the upper limit, when we take 1 over 8 and plug it in here. (5/4). So what do we have? We have 1 minus 16 times 1 over 60, so that's 64 there, and that's a quarter, and that's 3/4, right? So it should be 3/4. Yeah. I think it's 3/4. Okay, so let's take a look. Let's follow the white rabbit over here. So we have negative 1 over 32, integral 1 to 3/4, and then you have your u to the negative 1/2 du. So now that's, oh, and now we are going to switch back these limits to put the smaller one down and bigger one up, and that's where we lose this negative sign. That was actually in 5.4, one of the formulas that you guys are supposed to learn about this whole switching the limits. And we have u to the negative 1/2 du. Okay, so that's 1 over 32. We are adding 1, so that's u to the 1/2 divided by 1/2, computed from 3/4 to 1. And that is 1 over 32 times 2 square root of u from 3/4 to 1. All right, so that's 1 over 16. We have square root of 3/4 minus square root of 1. And it's 1 over 16 square root of 3 over 2 minus 1. And what you can do is find the common denominator. I mean, this is already an answer, but you can do a little bit better, because you can do common denominator here and then push that common denominator outside, or force 16 in, whatever. Root 3 over 2 over 32. I hope that my MATLAB would take this as well. It's definitely not going to take this one. I know that for sure. But maybe the one in the oval, maybe. And all I did is I just found common denominator here, right, is 2, and put those together so I can have that common denominator combined with 16 into 32. It's an algebra flex. Not a big deal. Guys, that's u sub. We're going to stop with the u sub here. We are going to review u sub next week a lot as well, with the rest of the integration and stuff. But now let's switch to the exam 3 review, which is coming up in 2 days, right? It starts on Friday, so let's talk about that. So, bye YouTube.